Hello everyone, welcome to Dakshana e-classroom program. So in today's lecture we are going to start a new chapter, and that is fluid mechanics. It's a little bit important chapter, and more than that it's actually quite easy. There are simple, like straightforward things, concepts are there, just learn them and learn how to apply. I hope you will find them easy and you will be able to apply, you will be able to solve questions. So in this chapter, first we are going to see what is actually fluid and what comes under fluid, what we do or how we define fluid, and then we will try to understand more about fluid, means its nature, its properties, and like when fluid is there, how does it apply force, does it apply pressure, how it apply pressure, and in which direction, what are the properties. So like broadly if we look at it, then fluid mechanics, basically it is further divided into two categories. One is when, let's say, fluid is at rest, then how it is exactly behaving. Another case when, let's say, fluid is flowing through a pipe or fluid is simply flowing. In that case, how exactly it behave, what is its behavior, its manner exactly. So all those things we are going to study in this chapter. So let me start first with the definition of fluid, how we can define fluid, or what is the exact meaning of fluid, is it. So simply I can say the fluid, any substance, is it, or material, substance which can flow. In simple terms, I can say substance which can flow can be defined as fluid, and it doesn't have any fixed shape. It simply acquire the shape of the container in which it is filled. So fluid doesn't have any shape. And one more thing about it, that it cannot bear any amount of shear stress. If you are not aware of the shear stress term, you will study, you will learn about shear stress in elasticity chapter. So fluid has property that they can't bear any amount of shear stress, but yes, they can bear a large amount of normal stress. So normal stress, longitudinal stress, fluids can bear, but shear stress they cannot bear at all. That is like one of the property. So this is how we can define fluid. In fluid, what comes under fluid is basically, so there are mainly like all liquids, you can say, and gases have these properties. So liquid and gas both comes under fluid, is it. So in this chapter our main focus will be on understanding the behavior of liquid as fluid. We will focus less on gas mainly we talk in terms of in another chapter, that is basically thermodynamics. So our focus in this part will be primarily only on liquid. So fluid here we primarily means liquid, is it. So fluid here which has both like liquid and gases. Then what is fluid mechanics? Fluid mechanics is basically study of fluid, is study or understanding fluid is termed as fluid mechanics, or you can say the branch of physics which deals with the study of fluid. So fluid mechanics, you can simply understand mechanics, it is a branch of physics which deals with the study of fluid or about fluid. And here, like as I told, fluid we broadly categorize into two categories. When once understanding about fluid when it is at rest, another case when it is in motion. So for that we define hydrostatic. So hydrostatic, it's basically studying about fluid or studying fluid when it is at rest, that we define as hydrostatic. Again, you can say branch of physics which deal with the study of fluid at rest is termed as hydrostatics. And next comes hydrodynamics. This is also branch of physics which deals with the study of fluid when it's in motion. So this is when, like, study of fluid when it is in rest, we termed as hydrostatics. When fluid is in motion, we deal with that study or study of fluid when it is in motion. That branch is termed as hydrodynamics. Cumulatively, these two form a combining form this fluid mechanics. Fluid mechanics means understanding the nature, understanding the behavior of fluid. And fluid, it's simply a substance which cannot bear any amount of shear stress, which can flow or which can take the shape of the container in which it is filled. So this is just definition of fluid. Then about properties, what else, like what are other thing or what are other properties in terms of those we can like define, we can differentiate between two or more than two fluids, is it? So when fluid 1, fluid 2, and then what are other properties? So let's say properties of fluid. So one term like mass, that we already understand, amount of substance, volume, how much space it is occupying, and more than that, the important thing is density, right? So density of fluid will be equal to, it's denoted by letter rho, and that is equal to mass divided by volume it is occupying, that is, so this is m divided by v is the volume, is termed as density of fluid. Next is relative density. What is relative density? So relative density, it's defined as density of substance divided by density of standard substance. And more precisely, I can say density, it's also equal to, because fluid can be liquid and gas both. So if I particularly discuss about density of liquid, then I would say density or relative density of liquid, that will be equal to density of substance or liquid divided by density of water at 4 degrees Celsius. So this ratio is termed as relative density, right? Few more thing, like next is density of mixture. So if let's suppose we are mixing two fluids, sometime maybe in the proportion of mass m1 m2 masses, density rho1 rho2, then what will be the density of mixture? And another case, v1 v2 volume of fluid having density rho1 rho2, then what will be the final density of mixture? So let me calculate that. Okay, so density of mixture. So here there are two possibilities actually, two liquids of density rho1 and mass m1, density rho2, mass m2 are mixed. So whenever like density of mixture is asked, always the basic formula for density of mixture is total mass divided by total volume is the basic formula for calculating density of mixture. Total volume. So now here it's mentioned density mass. So we know actually density is equal to what? Mass upon volume. Then what I can write? How much volume of liquid one is mixed? So this implies V1 can be written as rho 1 by just m1 by rho 1. Similarly V2 can be written as m2 by rho 2. Now total mass of mixture, that is equal to simply m1 plus m2. Total volume of mixture, that is equal to v1 plus v2, that is m1 by rho 1 plus m2 by rho 2. Just substituting everything here in this formula, so I am getting rho mixture equal to m1 plus m2 divided by m1 by rho 1 plus m2 by rho 2. This can be rearranged, and this is m1 plus m2 multiplied by rho 1 rho 2 divided by m1 rho 2 plus m2 rho 1. Is it? So this is general formula for calculating density of mixture. If two liquids of masses m1 m2 are mixed having density rho 1 rho 2, then density of the mixture can be calculated by using this relation. So here we can talk about one special case. If let's say m1 equal to m2 equal to m, means if both the liquids are mixed in same quantity, same mass, in that situation density of mixture will become simply, here what we can do is, in this relation we can substitute m1 equal to m2, so it will be equal to what? 2m divided by mm can be taken out, cancel from here, it will comes out to be simply rho 2 rho 1 rho 2 divided by rho 1 plus rho 2. And the next case comes B, when two liquids of density rho 1 and volume v1, density rho 2, volume v2 are mixed. So when two liquids density rho 1 and volume v1, density rho 2, volume v2 are mixed, in that case rho mixture again is asked to calculate. So again basic principle, basic formula is this: total mass divided by total volume. So this we can write is equal to total mass divided by total volume. Okay, so here already volume is provided, and we know mass is equal to what? Mass is equal to density multiplied by volume. So this implies mass of liquid 1 is rho 1 v1, mass of liquid 2 is equal to rho 2 v2, and here I can write total mass will be simply m1 plus m2, that is rho 1 v1 plus rho 2 v2. Total volume is simply v1 plus v2, because here we need to express the density of mixture in terms of the quantity which is provided to us. So here rho 1 v1 rho 2 v2 are provided, then we need to calculate the final mixture density in terms of only these quantities. So mass I can't use, m1 I will be using only in terms of density and volume. So here by just again substituting things, rho mixture total mass is this is rho 1 v1 rho 2 v2 divided by total volume v1 plus v2. This is the formula for density of mixture. So here also I can talk about again a special case. What is that? When v1 equal to v2 equal to v, means two liquids of density rho 1 rho 2 are mixed in equal volume. In that situation here I will substitute same thing, mixed. So make sure, so rho 1 rho 2 are definitely different. V1 equal to V2 is substituted V, so here will be like V taken out, and V plus V, it will be 2V, and then simplifying it we get rho 1 plus rho 2 divided by 2. So it's like average of density of two liquids. If liquids are mixed in equal volume, then this is the density. Next comes, because we are going to deal about fluid, this is density is one of the important property of fluid, so we should have like more idea, some idea about this also, because sometimes these small things can be also asked in your exam, so you should have like idea about that, how we can deal, how we can solve, and simple things are there. Just remember this relation. This is the approach in case you are forgetting things, you are like not able to, then or it will be easy, it will be help you in understanding that how exactly it comes, because if you just directly looking at the formula, then it will be like difficult for you people to even remember, is it? When you know the process behind it, how it is exactly derived, from where we got, I think this is what I believe, that it make things even easier, you feel like more confident about it, and in that case it become even easier to remember the formula also. So this is about density, calculating density of mixture. Next thing is density actually also depends, I'm like, is it constant for a fluid, or does it depends on some parameters? So the point is, yes, it depends. And what are those factors which affect the density? The two factors which we are going to study primarily, that is temperature and pressure. So let's see how density varies with temperature and pressure. Okay, so next is variation of density of fluid. So there are two parameters or two factors which affect the density, that is pressure and temperature. So let's talk about first variation of density of fluid with temperature. So we know already rho is equal to what? Mass upon volume. So let at T0 temperature, density of fluid is rho naught, or I would say the volume is V naught. And here we will need one more term, that is called, this is gamma, we call it gamma or gamma. So its gamma is called thermal coefficient of volumetric expansion. So how actually like with change in temperature density changes? Because we know density is equal to what? Mass upon volume. If we are changing the temperature, then you must be clear with that mass doesn't change, is it? Mass does not change. Whether you're changing pressure, temperature, whatever else, like anything else you can change, in any condition, in any case, mass of the substance remains constant until unless you are directly removing some substance from that. In that situation, mass will remain like change. Otherwise, we are like not removing that, then in case mass will remain simply constant. Volume will change by changing temperature. So here that like a straightforward thing is there. So density is direct, I can write inversely proportional to volume. So let's say let at temperature T naught plus let's say delta T, density become rho prime, is it? Or let me write it rho. At T naught its density is rho naught. Then what? Okay, rho is inversely proportional to V, so this implies I can write rho by rho naught will be equal to what? V naught by V. And if gamma is given as coefficient or thermal coefficient of volumetric expansion, in that situation, if V naught is the volume at temperature T naught, then V can be written as V naught 1 plus gamma delta T. So this can be substituted here. This implies it's V naught divided by V naught 1 plus gamma delta T. This is the changed volume on heating the liquid by temperature delta T. This can be rearranged, so v naught simply getting cancelled out, and I'm getting rho is equal to rho naught. This is 1 plus gamma delta t. As this is also expression, it can be further simplified more. Rho is equal to rho naught 1 plus gamma delta t power minus 1. It's 1 plus x power n is equal to minus 1 by binomial expansion. Because x quantity is less than 1, this gamma delta t is a small quantity, so by that I can write rho is equal to rho naught 1 minus gamma delta t by ignoring other higher order terms. This is the final expression, final relation of variation of density with temperature, gamma delta t. Right, so that is how you should be clear. Remember this result and this result also. So this is how the variation or density of liquid changes with rise in temperature. So here, if delta T means if it is cooling down, in that situation what will happen? Your delta T will be negative and density will increase. So here you can say density decreases with rise in temperature, is it? As volume increases, density decreases with rise in temperature. And here you must be familiar with one exception about water. In case of water, the density variation is a little bit different, rho versus temperature, is it? So initially it comes like this and then it goes like this. I mean it's about volume. Density, actually it's this way, is it? So at 4 degrees Celsius density of water become maximum, and before that density will be low. If you are heating it further, density will be low. So for water it's exception, otherwise in normal terms we can say density decreases with rise in temperature. Next is a variation of density with pressure. So let me just erase this part. Okay, next is variation of density of fluid with pressure. So again, with change in pressure, your mass is not going to change, your volume will change, and that will result in ultimately change in density. So let me consider that at P0 pressure, density of fluid is rho naught. Is rho naught, and here we will need one more quantity that is called B. It's called bulk modulus. If you are not familiar with this term, then you will be taught this in elasticity chapter again. Bulk modulus of fluid. So here it's related. Now what is happening? Let's say P0 is the temperature and P0 is the pressure and corresponding density is rho naught. And if pressure is increased, then what will happen? If your pressure applied is more, then it will contract, fluid will contract, is it? Compressed. So pressure is increased implies volume of fluid will decrease, and the relation between these two, so if delta P is the change in pressure, and let's say corresponding change in volume. So if delta P is positive, more pressure is applied means volume will be negative. So change in volume delta V is equal to delta V, and it will be a negative quantity. So that's why I have applied placed one more negative, so that this quantity become now positive. Now from the relation of bulk modulus, this is equal to delta P, that is pressure stress or bulk stress, divided by strain delta V by V minus. Now because delta V overall quantity will be negative, to make this quantity positive I have multiplied with one more negative sign. So here this implies again at delta V by V is equal to what? Delta P by B minus, is it? And in this situation again I can write rho inversely proportional to V. So at P naught pressure, rho naught is the density, let's say at pressure P naught plus delta P with rise, density I will say become rho. Then again I can write rho divided by rho naught will be equal to what? It's V inversely, so it's V naught divided by V. In this situation your volume will decrease, is it? So density must increase. So in this I will write this is equal to V naught divided by V minus delta V. Clear? I will write it better, V naught minus delta V, and then let me substitute. So V rho divided by rho naught, this is V naught divided by V naught. If I simply divide numerator denominator by V naught, then what I will get? Simply it's 1 divided by 1 minus delta V divided by V naught. That I can substitute delta V by V naught, it's equal to this quantity. So this will be 1 by 1 plus delta P divided by B, is it? So rho is coming out to be now rho naught divided by 1 plus delta P by B, is it? And with rise in here, because now this quantity was positive, is it? And because already I'm subtracting it, so I missed one negative sign. Otherwise I will, let me write it simply delta V, automatically it will be negative. So in that situation it will be this, and delta V by V will be coming this way. In that case it will be minus, and again by rearranging it's coming out to be rho naught 1 minus delta P by B power minus 1. Again expanding by binomial expansion, ignoring all higher order terms and getting it, because NEET students, you might be having problem with understanding this expansion. In that situation what else you can do is, one way is I am writing this 1 plus x raised to power n for x less than, or you can say very less than 1. This is 1 plus nx plus nx into right, n into n minus 1 into x square plus by 1 factorial. Basically this is 1 factorial, 2 factorial, n into n minus 1, n into n minus 1 into n minus 2 x cube by 3 factorial, so on. I'm also actually forgetting, just wait, let me tell you. Okay, so yes, that was actually correct. So 1 plus x raised to power n for x less than very less than 1, it can be expanded in this manner. And here if x is small, then x into x will be even smaller. X into x into x means x power square will be, x power 2 will be even smaller than this quantity. Cube will be even smaller than this quantity, like even smaller. So we ignore all higher order terms, then we write actually this quantity is simply equal to this by ignoring, making it to 0 and so on up to infinity. So 1 plus x raised to power n become 1 plus nx, because 1 factorial is simply equal to 1. So that way this quantity is almost equal to this. Just for your understanding purpose, you will not require to explain this to anyone, so no need to even remember if you are not understanding, nothing to worry. For your explanation I have written it in this manner. So the thing is, this can be expressed in this, because this simply power multiplying in power minus 1, and this minus 1 will be your n, so it will be like 1, my n is minus 1 into x. So that way I can write rho is equal to rho naught 1, and here minus and n is minus 1, so minus will become plus 1, and delta x is delta P by B. So this will be the variation of density of fluid with pressure. So where delta P is the rise in pressure of the fluid and B is the bulk modulus. So that is how, and like this is the final relation, final variation expression for the variation of density of fluid with rise in pressure, and this is all about density, and it's like density of mixture and variation of density with pressure and temperature. Try to remember these relations. This was all your explanation that how exactly it comes. Again, the point is that for medical students you will not require this derivation, but I hope it will help you in understanding that how exactly things comes up to this point. You need to remember the final result that I'm writing in basically this bracket, like this box. Is it? So let's continue with the application and more things about it. Okay, so next one of the very important parameter that we will be like dealing a lot, that is called pressure. So let me first tell you what is exactly simple the meaning, the term of pressure. So if I say, let's say this is some plane having some area A, then if force is applied along it, is it? So when the force is applied normal to the plane, that force is termed as thrust force. Thrust force. So a force applied normal to the surface is called thrust force. Actually the fluids, is it, all the fluid, if you consider any surface like a fluid whatever the surface it is in contact, fluid always apply a force perpendicular or normal to every surface. So the force applied by the fluid will be always thrust force, is it? It never apply a force along like tangential direction or at some angle. It always apply force by the fluid will be always normal to the surface. So this apply, it's called always thrust force. Then pressure is simply defined as pressure is equal to its thrust force per unit area, or you can call it pressure is equal to thrust force divided by area, that is simply called as pressure. So this can be written as simply F thrust divided by area. This normal force will be also called as thrust force. Simple definition. Unit, it's easy. This is Newton per meter square. Newton per meter square will be the unit. Another point here is that pressure, whether it's a scalar quantity or vector quantity, pressure it's not, because it seems like force, like vector quantity, area also vector quantity, but still pressure it's not a vector quantity, or as the vector addition of pressure is not added vectorially, is it? So that's why we normally call this pressure, it's a scalar quantity, it is a scalar quantity. And in case of fluid, if it is applied, it transmit or equally in all direction at any point. If you look, I will tell you those things or properties of pressure by the fluid, I will tell you about that. Then what happen actually in any point, is it, inside the fluid, but the applied pressure will transmit equally. So because of that, like it's also sometimes like if it is asked like pressure is a scalar vector, and then it's also it is a tensor actually quality. So it's definitely not, you can categorize it in as a scalar or tensor depending on like what is exactly given to you, but it's not a vector quantity because it's not pressure addition is not, pressure is not added vectorially. Means it doesn't follow triangular and parallelogram law of addition. Parallelogram and triangle law of addition. Okay, so and inside fluid, pressure applied transmitted equally in all directions. These are few properties of the pressure which differentiate it from vector quantities. So that's why it's like simply sometimes we call it scalar quantity where it's talking about vector or scalar, or it is also called as, because of these properties, it is also called as tensor. So that is simple definition. Simply thrust force per unit area is called pressure. Next thing is, like, we know the atmospheric pressure, is it? We hear it atmospheric pressure of PATM is equal to atmospheric pressure Many of you might be even remembering its value is 1.013 into 10 to the power 5 Pascal. Yes, I was talking about its unit. So unit is Newton meter square, and this is also called 1 Pascal, denoted by PA. So 1 Pascal also means 1 Newton per meter square. That is also termed as Pascal. So PATM or atmospheric pressure, this is equal to 1.013 into 10 to the power 5 Pascal. What it mean actually? Like, do you know that how, from where it come exactly? So let me tell you, explain you that. So basically this atmospheric pressure, you know, actually around Earth there is like what gases are there, is it, up to some height. So it's sort of like the weight of that gas column, is it, the force or weight of that gas column, gas up to starting from Earth surface to the like point where the atmosphere is spreaded, weight of that air column per unit area is that pressure, and it's equal to this much. So let me just write that. Okay, so the atmospheric pressure, it is actually can be defined as, it is numerically equal to the weight of column of air extending from Earth's surface to the top of the atmosphere, that weight per unit area. So here for practical things, like, let me tell you, yes, it is definitely sure that the density of air or atmosphere is not constant, is it? If around the Earth surface density is rho naught, then as we are going around 6 kilometer, density become rho naught by 2, half of the, and around 12 kilometer it become even like rho naught by 4. So in this manner density of air column keep on, or density of atmosphere keep on decreasing. But still, if I just for a calculation purpose, I can say, like, say the density of this atmospheric air is constant rho naught, and let's say its height is h, then what will be the mass, like area of cross section, A. Then I can write weight of air column that will be equal to what? Mass. First mass is density multiplied by volume, so volume is area into height h multiplied by, so this is into g is the force, and divided by area, that will be your atmospheric pressure, and this comes out to be rho naught into h into g. And if we take the rho naught, rho air, atmospheric density is 1.3 into kg per meter cube, is it? And we know already atmospheric pressure, the value of P comes out to be 1.013 into 10 to the power 5 Pascal. So in this manner we can calculate even the roughly or average height of the atmosphere, which calculating from this way, it comes out to be h is equal to what? P naught divided by rho into g. This is 1.013 into 10 to the power 5 Pascal divided by 1.3 into 9.8, which comes around 8 kilometer. So that doesn't mean the atmospheric the atmosphere around the earth is only extended up to 8 kilometer. This doesn't mean that atmosphere around Earth is extended only up to 8 kilometers. As I told, this is just for roughly calculation and make you understand what exactly it means. But the practical thing is that simply the pressure that we are experiencing or that we study, that atmosphere pressure, this is in simple term is equal to the weight of air column of the atmospheric air extended from surface to the top of the atmosphere, is it? So if like just normally we take around the earth, the density of the air is 1.3 kg per meter cube, but it's because it's not constant, is it? So that's why from this we get around the height of the atmosphere will be around 8 kilometers. But that was just rough calculation. Practically or for practical purpose, for practical, is it, study and all that, we take the maximum height of atmosphere, or we say the atmosphere is extended up to, is it, is extended up to around 1200 kilometer, because density keep on decreasing. So simple term, atmospheric pressure means that we see 1.013 Newton per 5 Pascal. This is equal to the weight of air column that is extended from Earth's surface to the top of. Okay, next, pressure due to fluid. So pressure, simple term we understood the meaning of atmospheric pressure, and let's talk about pressure due to a fluid. So let's consider this container, and in that some liquid is filled of density rho. So first few things about the property of liquid is that definition of fluid is that what, that it can't bear any amount of shear stress or shear force. It cannot bear, then how it can even apply? So means pressure or force applied by the fluid on any surface will be always normal to that surface, doesn't matter what is the orientation of the surface. So what it mean exactly? So here if I consider, let's say I am considering one surface in this manner. Let's say this is the surface oriented like this. Then force applied by this liquid will be in this direction. Thrust force will be applied always normal to that surface. Similarly, if I take a surface, hypothetical surface in this direction, then force applied by the liquid will be still in this orientation. If I consider one surface here, then force will be applied still normal to this. So means it is the property of liquid that liquid always apply a force normal to any surface, is it, in contact. It cannot apply force to any surface at any angle. So in this situation, if I talk about the force or pressure at this wall, it will be normal to it. Pressure at this, it will be normal to it. Pressure at this point will be normal to it. Pressure at this point will be normal to it. So this is the basic property of fluid, that whatever the surface is, the fluid is in contact, always it will apply force normal to that surface. So similarly, just consider this condition. Let's say a fluid is filled in this type of container. Okay, so let's say this is the one container in which some fluid is filled, then it's up to here. Then what will happen actually, again at this point the force of pressure by the liquid will be in this direction. At this point it will be in this direction. At this point it will be in this direction, normal to it. Always it apply force normal to it. Similarly, if you consider another case of, like, let's say this, is it, let's say just this container, and where something like this, and fluid is filled up to here. Then what will happen at this point? It will apply force in this direction, in this direction, in this direction. At this point, the force by the fluid will be directed in this direction. Is it? So this is the basic property, and it's very important. You should keep that in mind. So the liquid always apply a force normal to any surface in contact. So that means I can say the pressure applied by a liquid will be always normal to any surface in contact, doesn't or does not depends on the orientation of contacting surface. This is about fluid. Next things come is that how much exactly pressure it apply, is it? So let's see the variation of pressure with height, is it? So for this case, I can consider again one container, let's say this, and it's filled up to some height, some liquid is filled up to this height. Now what I can consider here is that, let me consider this is a hypothetical cube of same liquid, is it? So this is the container filled with liquid of density rho, and here I am taking reference, and this height, let's say taking y, and this is taking dy. Its area of cross section is A. Okay, so top area of cross section is A, and then I can take, let's say the pressure at this point is P, and pressure at this point is P plus dP. So right now I am talking about the variation of pressure. Another point here, pressure is equal to P naught. So atmosphere pressure, because this is open to atmosphere, so we take that atmosphere pressure as P naught. Now simple thing, here I am trying to explain the variation of pressure in the liquid with height or with depth. So what is that? Consider a hypothetical, or not exactly, consider a fluid column, fluid cube of same just wait, consider a cube of same fluid in rest. Another thing is, because this complete liquid is at rest, so definitely every, like I can say, small part of the liquid will be at rest. It will not be the condition that this part of the liquid is moving in this direction, in that direction. That will not happen. So what I'm considering, you can say just an imaginary cube that is also made of same liquid. So what I can say, this cube will be also in equilibrium. This cube will be in equilibrium, right? Now what I can write, let's calculate the force on it, is it? So force balance in vertical direction. Then what will happen actually? Net downward force, I can write P plus dP multiplied by its area plus its weight. Weight will be equal to what? Rho into A into dy, density into volume multiplied by G, its weight. Upward force, it's P into area, and that should be equal to what? 0. So PA, this gets cancelled. I can write this PA plus dP into A plus rho A G into dy minus PA equal to 0. This PA gets cancelled, and let me bring this term that side. So then I am getting, and area I am also cancelling out. So dP is coming out to be minus rho G into dy, and this implies dP by dy is equal to minus of rho G. What does it mean? That mean, because here I am measuring y from the bottom of the surface, so this is implying as you are going up, is it, means the change in pressure with increase in y is negative, means as you are going up the inside the liquid, your pressure is decreasing, right? That is the meaning of this. So negative sign is implying here, let me just tell you that. So dP over dy is equal to minus of rho G. Negative sign means as y increases, pressure decreases, right? Next, exactly I can calculate also that from top at depth of h what will be the pressure, because that is also quite important. So let's say this is filled up to here, and again I am having this. So this is, I am taking, let's say y1, and this I have already defined as dy. Then I will, okay, so finally I got this expression. What can be done from here? dP can be minus of rho into G into dy. Let me integrate it both sides, and from here where y1 to y2 I can write p1 to p2, then integration of dP will be p, substituting limit p2 minus p1, minus rho G, integration of dy will be y, again substituting the limit from y1 to y2, so we are getting minus rho G, this is what, y2 minus y1, this is p2 minus p1. I got general expression. Now let me take few points. So I am taking here, this is my point 1, and I am taking y2, this is y2 which is open, so p2 can be written as what, p0, atmospheric pressure. Y2 is this, and y1 I am taking here, and this I am taking basically h. So y2 minus y1 will be equal to what, h, right? And this is p2, and let's say here this pressure is p. Okay, so then substituting here I can write equal to p1. So p1 is equal to, this is pressure, p2 is equal to p0 minus p minus rho G, and y2 minus y1, y2 minus y1 is equal to what, h. Then P, I want actually pressure, this comes out to be, so bringing it this side and this side, so P is coming out to be P0 plus rho G H. So this is the variation of pressure with, you can say, depth H inside the liquid. So you can see H equal to 0 at the top surface, P will be simply become P0. As you are going down, it depends on like height or H, the value of H. So pressure inside the liquid depends on what factor? Its density of the liquid, value of G, and height H, right? So let me just erase that part. Okay, so now from here we got actually the expression for pressure inside liquid at any point, that is given by P into rho G H. So one thing is that from here also I can write, if I am considering 2 points at same level, then pressure is depending on what, rho and H, both are constant. So I can write from here also that pressure at same level in same liquid will be equal, is it? So first thing is pressure inside liquid depends on first density of liquid, and you can write depth of liquid. So means if I am considering 2 points in the liquid at same level, is it? If I am considering 2 points, let's say it's filled, and here I am considering 2 points. This is point 1, this is point 2. Both are at same level H. Then I can say pressure at point 1 will be equal to pressure at point 2 because it's simply depending on H. So this implies pressure at same level in liquid will be always pressure at same level in, I would say, because we will see sometime level will be same but liquid is different. In that situation, this condition will like I need to modify. So based on that, I am writing pressure at same level in same liquid will be always equal. Here I am trying to explain you everything, that how exactly things come, how we got this expression. You are supposed to remember the final result and the theory behind back, that why all this is happening, why, from where we got. That will help you in understanding and answering the logical questions asked based on this. You are not supposed to remember the derivation, the approach. That is just to make you feel better, make you understand that exactly how things are like derived, how we are getting this relation. So I hope you should find it better. I'm trying my best. So first thing is like at same, these are few properties, because liquid, their behavior is something different. You can't compare the behavior of liquid with the solid, is it? Solid behavior is different, liquid behavior. So what is the exactly behavior of liquid? I am trying to explain you point by point. You try to remember them. That will help you in understanding things properly. So here we understood that pressure inside the liquids depends on what? Height. Is it? It does not depends actually the weight of liquid here. Is it? Means I will tell you that point also. So another point is pressure at same level in same liquid will be also equal. This you can even counter like way I can explain you this is that, let's say this is the container. Then what is happening if you are considering one fluid element? So if pressure at this point is different than pressure at this point, then what will happen? This liquid element will experience some force. And how it is that possible? Is it? So let's say this is point 1, this is point 2. So if pressure, if P1 is not equal to P2, what it implies? This implies the liquid element will experience some force. That is not possible. Is it? So here pressure at same level in same liquid will be always equal. And another point here is that just consider one point inside the liquid. Is it? So what will be happening? Okay, so this is container filled with liquid up to here, and here I am considering just very small element. So on this I'm like, it's very small actually, its height you can almost neglect like this. Then what will be happening on this element? Pressure will be like, one pressure will be from this side P1, from top P2, from this side P3, and from this side P4. Is it? So if one of like, if all these are not equal, then whichever is higher, the element will be moving in that direction. But this is the same fluid element in a liquid filled in the container, then how the like it's moving by itself? That's not possible, right? So what it implies, what it means, pressure at same level, is it, will be acting in all direction. Is it? Pressure due to fluid is applied in all direction. equally at same level. So at this small element, very small element. First thing is, if we are considering just one point, then on that point pressure due to fluid will be this way, this way, this way, this way. At every angle in all direction pressure will be like equal. Another point at same level, if you are considering 2 or more than 2 point, pressure due to the fluid will be same. And pressure due to fluid does not depends on weight of fluid. It can be even greater than weight of fluid. Just consider the situation here. So I understood this is one container, and in this pressure here, so at this point pressure will be like P naught plus rho g h, if h is the height of this, is it? And you can write this will be proportional to its weight. If I am considering another case, let's say pressure is filled here, liquid is filled up to same level. So in this situation also height is what? H, same. So pressure at this point will be still P, it's equal to P naught plus rho g h. If same liquid is filled, same liquid, same density is filled. Another case, again consider it's at same level and fluid is filled up to here, same level. So this is also H, then pressure at this point will be also equal to P naught plus rho g h. So you can see in all situations the weight of the fluid is different, but still because it's depending on only height, even if I am considering a very small tube, is it? And here also fluid is filled up to this level, then pressure at this point will be P equal to again P naught plus rho g h. So it depends only on the height of fluid column, not on its weight. Pressure at same level will be same. Pressure at any point inside the fluid will be acting in all directions. Depending on the surface you are placing, if you are placing the surface in this orientation, pressure will be acting this way, pressure will be acting this way. If you are changing the orientation, pressure will be changing this way, acting this way. So changing the orientation of the surface, always pressure will be acting normal to every surface. So these are few points about the pressure inside a fluid. Next comes is its measurement, and how we say like I told already, the pressure, atmosphere pressure is 1.013 into 10 to the power 5 Pascal. Exactly how we got it actually. So we have some instruments to measure the pressure, and that is called barometer and manometer. So let me explain those in the next class.